Good evening, everyone. I have a little treat for you today. It's a topic that I think is really interesting in this nano degree. It's how neural networks are used in deep reinforcement learning. It's sort of really a core idea for how everything is done in deep reinforcement learning. So understanding this topic is really important, and I think tonight's webinar will give you some insight into how all this kind of works behind the scenes. So with that, let me close the presentation here and we'll get started. Okay, so again, the topic's about neural networks and deep reinforcement learning, and really concentrating on how neural networks are universal function approximators and how that idea is used in a lot of the different algorithms that you'll see in throughout different deep reinforcement learning methods. So here's a couple of objectives for tonight. First one is just to provide some insight on neural networks in general as universal function approximators, and then talk about how that particular property is useful in deep reinforcement learning. Most of this information came from a single source. It's a very interesting webpage. I really encourage you to take a look at this. It goes into a lot more depth than what I'll go into tonight, but it's really presented in I think, an excellent way. And so I relied on a lot of their ideas and some of their graphics to put together tonight's presentation. It's from the University of Tartu Institute of Computer Science. It's a university in Estonia, one of the Baltic countries. I'd never heard of that university before, but they were actually founded like in 1630 or something. It was like they've been around for a long time. Okay, so first topic, neural networks in general. So, most of you have all had some courses in neural networks, sort of a foundation piece of knowledge that you're expected to have before you can really understand anything in this deep reinforcement learning area. So I won't go into a lot of detail on this, but just as a reminder, what the particular property we're really interested in for most of what we do in deep reinforcement learning is this concept of using a neural network as a function approximator. So you'll see throughout the course a lot of different algorithms, especially once you get past the first deep Q learning before you get into DQN and all the things that come after that. Initially, neural networks aren't used as kind of just a simple temporal difference updates and those sorts of things, but very quickly we'll get into using neural networks to approximate the value functions, either the V functions or the Q value functions. So how is that done? Well, again, as you probably know, neural networks can approximate any function. They're universal function approximators. So given a set of inputs in the input neurons, and there can be any number of these, if you have three inputs here, that lets you support up to three different variables to be input into your function, a function of three variables. If you had a function of 10 variables, you might have 10 inputs there. So usually the inputs in deep learning are going to be either states or actions or some combination of states and actions. Then what we're estimating are Q functions typically. But again, neural networks can estimate any function. And in fact, a really interesting property is that a single neural network can actually simultaneously estimate any number of independent functions. The only requirement is that each one of them needs to be a continuous function. So if there's discontinuities, then the network will have some difficulty around where those discontinuities are. You get more error in those areas. But it's sort of as long as you don't have very many of those, or they're isolated, and you still often will see them appear in functions that you approximate. But that's kind of an aside topic anyway. What's the important thing here is that a single neural network can estimate any number of functions, and so you could have f1 here as a function of x1, x2, x3. You could have f2 as a function of those same three inputs, and in fact, any number of functions. You could add another output neuron ad infinitum for as many functions as you'd like to approximate. And the cool thing about it is you put the inputs in, run one forward propagation step, and every one of those approximated functions get calculated in that one pass. So it's a pretty cool property, and something that we'll see used here in deep reinforcement learning in a second. So there's a trade-off here. These neural networks, they can approximate any function. They are universal, but if you want to be really precise in how well you want to estimate those functions, you have to have a lot of neurons, and you can get essentially as much precision as you want by adding more and more neurons. And I guess if you add an infinite number of neurons, you can get infinite precision in those estimates. But there's a trade-off here in that you get to train this neural network with backprop, and as you know, that can be a slow process. Every step of backpropagation takes time to go. We feed the data forward, calculate the error, feed the error back. There's a lot of updates to be done. The more neurons that you have in your network, the longer that takes. So there's just always this trade-off that you'll see, forever when we work in this field of precision versus how much time you're willing to spend training your neural networks. So let's see, did I skip forward here? Let's see. No, we're good. Okay. So before we leave the general topic of neural networks, I just wanted to touch on another type of network besides the standard feed-forward fully connected network, and that's a convolutional neural network. These are used in a little bit different way. You'll see the fully connected feed-forward networks used in every function approximation just about in this course. Sometimes, though, your input space may not be just a set of discrete states or actions. It might be an image. For example, a really famous paper by Min that you should read if you haven't read it yet, but you'll certainly be introduced to it in this course. It's a fascinating paper. It kind of kicked off this whole deep reinforcement learning knowledge area, and kind of showed what can be done with this paradigm. So those researchers were taking as their test case a bunch of Atari video games. I think there were like 49 different games, and they actually fed into the network the actual screen shots from Atari. So whenever you're inputting imagery like that into your neural network, it might be input from a game, it might be input from a sensor, a camera, LiDAR if you're doing like an automobile autonomous vehicle application. Any number of things could be represented as imagery, and you might want to use that as part of your state space. Then you need to be able to get that data in and extract features from it that can represent the state information. So convolutional neural networks are used for that purpose. Now, this particular one I've shown here is just something that's, you've probably seen this before. It's an MNIST example. The idea here is a classification example where you want to classify digits. So I just put this up because I think most of you are familiar with this, but you'd input a digit like 2 in this example to the input. The actual pixel values would come into the network. Typically go through a number of steps of convolutions and max pooling layers of different sizes. And the convolutions, that kind of extracts the different features that you use, and every layer of this that you do, you get higher and higher level features. And one of the reasons for the max pooling is both to reduce the size of the space that you're working with, and also to give a measure of translation invariance. So this particular example, again, is a classification example. You don't see this implemented exactly this way in deep reinforcement learning, but we'll show in a bit what some of the differences are. Okay, so now let's move on to away from the general neural network discussion into looking at some specific things and how these neural networks are used in deep reinforcement learning. As the first example is probably the first place that you'll see this used. I think it might have been one of the earlier topics in the textbook, and certainly in the Udacity video courseware. The first place that you see this used is in Q-learning, sort of a natural extension from Q tables that is a simple tabular expression for state and action combinations, where every combination of a possible state and action will get an entry in the table, and then the Q values are accumulated in those table entries. And that works fine for really small kind of discrete spaces. The taxi cab problem that we talked about last week, is an example of that. You had a fixed set of cells the taxi cab could be in, a fixed set of actions it could take. It's very defined, small numbers. You don't need a neural network to solve that problem. But for some things, some more difficult problems, we'll find out that actually storing every possible Q value in a table is not feasible. So we'll see how neural networks are used instead. So just to review, the Bellman equation, the most famous equation in all of deep reinforcement learning, I think. In this case, it's the Bellman equation for Q value, estimating Q value. And you can see that the Q value for a particular state action pair, it's equal to the reward that's received for taking that action in that state. That reward comes from the environment. The environment also feeds back a next state value to you. And so what the Q-learning does is basically use this this definition for how to update a Q value, what the definition of a Q value is, by taking the discounted return and adding that on to the immediate reward that you got. So that discounted return is the return of the state that you're sent to and the best action you could take from that state. So it's sort of like a one-state look-ahead to update the current state with a discounted value of that look-ahead state plus the immediate reward. So that is the Bellman equation. It's again, you'll see it in different forms and different representations in different ways in this course, but this is the most simple, I think, definition of it here. So the next slide is, so as I started to mention earlier on the earlier slide, when you start getting too many states or you have too many actions that you have to be concerned with, or you have states that maybe not be discrete. If you have continuous states, essentially you may have an infinite number of states. So in these real world kind of problems that you want to solve, a Q table kind of approach isn't going to work. So the point is that even though you have all these infinite number of states, a lot of those states, most of them probably, are very rarely visited. Some may never be visited. A lot of them may never be visited. But you want to be able to estimate any Q value for any state that could exist in the network. And in fact, it would be cool if you could actually estimate Q values for states that you've never seen before. Now, with the Q table approach, you never update an entry in the Q table until you visit that state. With a neural network function approximator, we'll find out that you can actually estimate values for states that you have never seen before. That's kind of a really neat thing that you get here with the neural network implementation. So the answer to this is, as you guessed, probably by now, is that we have to estimate what this Q value is. It's a function. So in order to estimate this function, we'll use a neural network. Neural networks can estimate any function, so we're going to use it to estimate a Q value. So let's see how we do that. This slide shows what I would call a naive approach to the neural network architecture for Q learning. If you think about trying to estimate Q value for Q of SA, where your Q value is dependent on the state and the action you're taking in that state, well, if you feed in the state and the action into a network, you can have that network do its magic to estimate the Q value for that. And if you have something that will let you know a better value for what that Q value is and come up with a loss function, then you could train that network to get better and better at estimating those Q values. So that works great for estimating Q of SA, because you have you're given a state, you're given an action, you want to estimate that Q value, you do one forward prop step and you get the Q value. But remember from the Bellman equation, let me back up one. So there's two things here, right, in the Bellman equation. You have the Q value for the current state, but you also need to know the Q values for the next state that you're in, and not just one Q value for the next state. You need to know all the Q values, one for each action that's in that state, so you can pick the action that gives you the highest return. So for estimating this part of the equation, using this naive implementation that we show here, you have to input a Q value with the next state and the next action. One of those next actions, get a Q value, save that Q value away, put that same next state in with a different action, estimate the Q of S prime A prime for that action, save that Q value away, and do the same thing for every possible action that could be taken in that state. And then every one of those would be a feed forward pass through the network And then at the end, you will have collected up all those Q values, and you can pick the one that's max. So that would take quite a bit of time if you had a lot of actions. So what Min et al. Did is really something kind of interesting. Remember how we talked initially about how a single network can take a set of inputs and produce any number of function approximations? So they took that property and said that rather than feed in a state and an action, let's just feed in a state and have the network do its magic to produce the Q values for every possible action you could have in that state. So in one pass, you get the Q value for action 1, you get the Q value for action 2, you get the Q value for action n, for however many actions you have. And all that happens in one forward pass. Really cool. So now basically you can use this setup to estimate Q of SA by putting in the state that you have, run it through the network once, and then just look up in the Q value functions, pick the function that's the action that you were interested in, and that's your Q of SA value. But for the Q of S prime A prime, the next state, next action pairs, you feed in the state S prime, the next state value. You get all the Q values at once for all the different actions, and then you can just go through and pick the maximum one, and that gives you Q of S prime A prime, the max, the best Q value that you could get from that next state value. So pretty cool. You can use this one network setup to handle both of those in one pass. Well, one pass for each. So in order to train this network, you need to come up with a loss function. So the loss function I've shown you here is a typical one that's used. It's a mean squared error loss, one you see probably in a lot of neural network derivations. This one is based. So I lost the share just a second. Okay. So in this particular case, I've reproduced the Bellman equation here because it's an important part of this loss equation. So what we're trying to predict is this Q of SA value. And to predict that value, we're going to use the reward we get from the environment and the discounted maximum Q value we get for entering the next state, assuming we take the best action we could in that state. So we don't know either one of these. We don't know Q of SA, and we don't know Q of S prime A prime. So how can we update this network to do that? So, initially we just put in random values for all the weights of the network, but then over time, as we visit these different states, we start making updates to them, and the updates are based on this loss function. So the prediction is what we're trying to predict, but we know the value should be this reward plus the discounted value. So let's take the target, what it should be, subtract what we thought it was before, and use that as the error, the loss function. Since it's mean squared error loss, we'll square that, and then this little 1/2 in front, that's just a trick, as you probably remember from your basic neural network classes. The actual implementation of this loss function is a gradient descent. So we take the gradient, we take the derivative of this function, and it's just nice if you have a square value here, the derivative of that, you're going to multiply this function by 2. So having the 1/2 in front sort of makes that all go away and just simplifies the calculations. Okay, so pretty cool. We have a loss function now. So given a loss function, we can now go about training the neural network. So here's the training algorithm. This again is pulled from the University of Tartu's example. So the words are direct from their algorithm description. It's basically a 4-step process. We feed forward in that network, and I have a picture here in a second to kind of show this in a review phase here. But we're going to take the current state we're in, feed it forward through the network, get the Q values for all the actions. Then we'll do another feed forward pass for the next state as input, calculate the maximum over all those outputs to find the best action you could take, the highest Q value for that next state input. Now here's the trick in step 3 here. We're going to set the Q value for the target action to the A. So A is the one action that we are interested in, the one that was taken in the current state. And we're going to set its value to the target value, the reward plus the discounted max QSA that we calculated in step 2.
And for all the other actions on the network, we're going to set them to what they originally had from Q of SA, and set the error for all those to 0, but set the error for that one action that we're interested in to that loss value, and then get the gradient from that, and use that to update the weights to using standard backprop. So that's the basic algorithm. Pretty simple, really. Here it is again, sort of with the picture. I reversed the first 2 steps here. So first, I had you put in the next state value as input, calculate all of the next state actions, the Q values for all the next state actions that you could take, pick the maximum one of those. Then again, feed in the current state, S, have the network calculate all the possible Q values for all the actions that you could take. Only one of those is the one that you're interested in training on. It's the one that was taken. The Q of SA is the action A. You're going to set that Q of SA to the target from the Bellman, from the first set of Q of S prime A prime max values that you got. Leave all the rest of them alone. Set all the errors for all the others to 0. Set the error for this one that we had that we're trying to learn something about to that loss value, and do the backprop, perform gradient descent. So again, that's the basics of how Q values are estimated in a deep reinforcement learning using deep neural networks. You'll see this same kind of idea used in lots of different equations. Later on in the course, you'll get actor and critics doing different things, estimating actions to take, estimating values of those actions, all using basically the same basic thought of a universal function approximator to do the estimations. So this last section, I just want to do a quick overview of how convolutional neural nets are used in deep reinforcement learning. This is just a real short introduction. I think we have a whole lecture on this next week. But I just wanted to remind you about this Min paper. It input actual screenshots of the game board in grayscale, kind of reduced in size somewhat to 84 by 84 pixels, and then they had 4 frames of those 84 by 84 pixel images, so that they could track some time dependent changes in the state space. That's basically the state input. The state outputs here at the very last of these 5 layers of this network are 18 different outputs. Essentially what that says, I think, is that there's 18 possible things you could do in these Atari games. Again, they did 49 different Atari games. So across all those different Atari games, there were 18 different actions you could take. They might be, pushing the joystick forward, pushing it left, pushing button 1, pushing button 2, all the different things that you could do in the different games. So they came up with those 18 different possibilities. And they used the same network to train all 49 of those games. So this is a simple 5-layer network. You'll notice that there's 3 convolution layers to extract the features, and then 2 fully connected layers to actually do the standard processing for things we just talked about. So for this, you'll notice that there's no max pooling, which is kind of unusual, right? You always think about max pooling being in a convolutional neural network, but if you remember in a classification problem, you don't really know where the image that you're trying to classify might appear in the image, so the max pooling helps provide some translation independence. Here in this case, you don't have to worry about that, because the input screen is the input screen. It's not going to be shifted around. It's not going to be moved to a different location. It's always what it is. So there's no need to do the max pooling. So the author skipped that step just to kind of save some processing, and it's an unnecessary complication. And this is just a picture of that same network architecture you just saw. It has the 3 convolution layers, and then the 2 fully connected layers to get the output actions. So this particular network was essentially used to input imagery, and at the output of the network is the action to take. And the actions are basically probabilities. Use a softmax output on the output here, and you get the probability of each one of those actions, and you can use some randomness to pick them based on the probability distribution to pick an appropriate action each step. So that's it for today's webinar. Just as a summary, we reviewed neural networks and their interesting property as universal function approximators, and showed some examples how the neural networks are used in deep reinforcement learning. This first example was how Q values are estimated, not only the Q value for the current state, but also the Q value for the best action in the next state, and then how those two values are used together to update the Q of SA for the current state using the Bellman equation and the loss that you see here using standard gradient descent. So with that, be happy to answer any questions. Immediately following the live session, we'll have a Ask Me Anything session on what's the application? Slack. Thank you. So we'll switch over to Slack now and be happy to answer any questions there. And it could be about this particular topic, how neural networks are used, or anything else that you might be struggling with in the course. So we'll see you there. Bye.